Okay, hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. And in my very last video I talked about, well, I did a walkthrough, I tried to do a thorough walkthrough of the Jupyter notebook that was on the analysis of tracking evolution of entities with learning enabled, which is this one. And I had a look at the entity distributions, the lifespans of entities, the slopes and the positive slope ratio, and the summed utility plots. Yeah, all of the good stuff. And then yeah, and that was it. So after that, I'll be very honest, after having done that, I felt kind of lost, because I didn't know what else to do after this. And since I had spent so much time on trying to get all the values and the metrics and analyze the effects of enabling individual learning on the on the part of entities. Yeah, so I was lost, and then I had another idea, or another set of ideas, where and that idea was that I could change the learn rate and the learn candidates, or rather change the learn rates for each individual entity, and also change the way that the candidates are chosen. Yeah, that's the better way of saying it. So previously, this is how the candidates were chosen. We had a start decile and we had an end decile, and it would be from decile 0 to decile 0.1, decile 0 to decile 0.2, and then on and on and on until 0 to 1.0, and then on to the next one, which is where the start decile is 0.1, and then the end decile would continue on from 0.1 all the way up to 1.0, and then on to 0.2 being the start decile, and on until 1.0. And doing this would give us 66 candidate ranges, or rather windows and ranges. I'll try to use them interchangeably. I don't know if that's actually going to be more confusing or not. So yeah, the orange cells are the deciles that are chosen, and if 2 are chosen, it means that 10% of if 2 cells are orange, it means that 10% of the given world were chosen as candidates to learn. If there were if 10 of them were chosen, it means that 90% of them were chosen. If 4 of them are orange, it means that 30% are chosen. So that's how it used to be. But now I thought maybe I could also change the way that I choose the candidate ranges, or rather I change the way that I choose the candidates. and that is by just sampling from the entities in the world within a generation. So, a few ideas. Well, I know I'm going to sound like I'm all over the place, but please, well, bear with me, forgive me. So, it's change the way that the candidates are chosen, candidates or candidacy. I don't know how to spell. And also change the learn rate as well. So how to do this? First of all, well, so far this was done by just selecting Windows, and I could change this to just if this is the world of entities after the newborn entities were added, including newborns, and I could just number 1 select at random, and just random select, randomly select, for example, 0%, which means no learning would take place, 10%, 20%, and on and on and on until 100%. So any entity and every entity within the world at that point in time, within that generation, would have the same chance of being picked. So in terms of weights, that would be a uniform weight. The weights would be a uniform distribution. Second way of doing it is well, I would keep using the concept of weights, but I would still need to sample them without replacement. So I found a way to do that using Python random choices, because usually, not usually, the Python module that is random dot choices, well, random dot sample, that's what I use for this, but random dot choices, hold on, random dot sample is what I use for this without the parameter that is a list of weights, because that's what it does inherently. However, I cannot use random dot sample because it doesn't accept the argument weights. So I had to use the random choices, but random, not choice, but choices, because this one accepts weights. Because this one accepts weights, but also I've also had to find a way to work around the fact that random choices does not have the option to well, not allow replacement. I know NumPy has it, but I didn't want to use NumPy. I'm just trying to keep everything as simple as possible, as independent from modules as possible. So I found a way to work around that, and the weights would be, in this case, in the second case, would be kind of proportional, and by that I mean if I had the world here, again with the newborns added, and they would all be ranked from 1 to 3 to all the way to 1000 plus. It's not going to be exactly 1000, but 1000 plus, because the newborns were added just right before this, because it's add first, learn later. Add first, learn later. So anyway, then but in this case, let's just say it's 1000, just while keeping in mind that it could be more than 1000. So the first way of assigning the weights is proportions, or proportionate, or proportional, any word, any one of those words. So rank 1 would have and there are also two ways of doing this as well, to doing it proportional. First, the first one is favoring the tail, or the last entity in the world, which has the lowest summed utility score. And so the first way of doing this would be ensuring that the last entity within the world, the list of entities, ensuring that this one has the highest chance of being picked as a learned candidate, and ensuring that the second last one has the second highest, third last one has the third highest, and on and on and on, and the top entity, the head entity, would have a very small chance of being picked. So if it were to be graphed, it would look something like this. So it's the chances of entities being picked as candidates for learning are proportional, or proportionate, yeah. And a second way, the third way of doing this, another way of doing this is ensuring that the head entity has the highest. Should I just spell highest? It's not that I don't know how to spell highest, it's just a lot of work. Highest chance of being picked, and ensuring, and the second entity with the second highest summed utility score would have the second highest chance of being picked. I know there's an A missing here, and on and on and on. And the last entity in the world would have the lowest chance of being picked. So again, if you were to plot it, it would be something like this, but still proportional, in a proportional fashion. So two ways of doing it proportional: one where the tail is the highest, one where the head is the highest. And another way of the third way of weights is, let me just zoom in again. Third way of doing that is exponential. So this is a lot similar. So the first way of doing that would be, number one, would be ensuring that the tail entity has the highest chance and the head entity has the lowest chance. And if you were to plot it again, this is where the lowest entity is, the tail is, and for example, if this is where the head is, the chances of these entities being picked would look something like this. And so therefore, naturally, another way of doing it with exponential weights is, you guessed it, the other way around, where this is where the head is and this is where the tail is, and the tail would have the lowest chance of being picked and the head would have the highest chance of being picked. So that's 1, 2, 3, 4, 5. And the last one would just be, what's missing? Well, we always have the good old where this is the highest. Anyway, I did that wrong. And the last way of doing it would be ensuring that it is a normal distribution. So somewhere in the middle, if you are the median entity would have the highest chance of being picked. Oh wait, did I do this right? Yeah, I did that right. High chance, low chance. LC, HC, HC, LC. And so here, when using a normal distribution for the chances of chances of individual entities being picked, the median entity would have the highest chance. So this is high, and at the end, at both ends, for both for the head entity and the tail entity, they would have the lower, or rather the lowest chances of being picked. And if you're close to the median entity, you'd still have a very high chance of being picked, and that's how it goes. So there are 1, 2, random, give me red, random, proportionate, and another proportionate, exponential, another exponential, and normal distribution. If the tail entity is guaranteed to have the highest chance of being picked, that is called a tail favored. If the head entity has the highest chance of being picked, that's called a head favored. Same thing here. Oh god, I need a pen to do this. Tail favored. This is head favored. And technically this is median favored. Median, or should I just spell it mid? That's so bad. Oops. This is mid favored, or median favored. That's how it is. So there are 1, 2, 3, 4, 5, 6 ways of doing this. So that's for the candidates or candidacy. Okay. And for the learn rates, well, it's kind of similar. Let me just take a sip of water. Okay, suppose we have the world already with with the newborns added, and suppose that a certain percentage or a certain number of entities were picked as learning candidates. And each of these entities in the group called learn candidates would have a different learn rate. Now, again, the first way of doing that, the first way of doing that would be just for each entity that are picked, assign a learn rate, but at random, where learn rate is smaller or equal to 1.0, as in 100%, or bigger than or equal to 0, or 0%. But so from a uniform distribution, so that's how it goes. And because it's it would be using a uniform distribution where it's ultimately just a random learn rate, a learn rate that is sampled from a distribution that is uniform, which just will be random. I mumbled there. So learn rate that is sampled from a distribution that is uniform, which ultimately could be called a random distribution. So the learn rate doesn't have to be like every number between 0 to 100 or 0 to 1.0. It will just be 0, 0.1, 0.2, 0.3, all the way to 1.0. So just pick one. So this is random. The second way of doing that, again, is very similar to what we had here, because it's it uses the same concept, proportionate. Which means that before the learn candidates are chosen, plus NV, before the learn candidates are chosen, this is the first one in the list will be the head, or just the one of the newborns, the first one of the newborns, and the last one would be the tail, definitely. So the ones towards the head are very likely to have a relatively high or relatively higher sum utility values. So what happens here is, I say proportional because, again, number one, in a tail favored way, I could ensure that the learn rate for the tail entity is the highest and the learn rate for the head entity is the lowest. Now, because learn rate cannot go above 1.0, highest has to be 1 and the lowest has to be 0 or very close to 0, and because it's proportionate, it's a straight line. So this is the tail favored way. And the other one, of course, is the head favored way. where I would have the same setting over here, and I'll just draw it again, and I would ensure that the head entity has the maximum learn rate and the tail entity has a lowest learn rate. So this is a straight line again. This is the proportionate. So that's 1, 2, 3. The third one, it's exactly the same. Third one would be exponential. And that would be in a tail favorite situation. I would ensure that the tail entity has the highest learn rate, and the head entity has the lowest learn rate, but it has to be a it has to look like an exponential distribution. So this is 0, and the highest value should be 1. So, and it has to look very exponential, like this. I know it could be more exponential like that, but let me... I suck at this. No, why is it so hard? There. Now this point is 1, and this is the tail. And this is the head. So either 0 or very close to 0. Very low value for the learn rate. And again, I am going to repeat myself. Another one for this would be the head favored, which is where the head entity would have the highest learn rate, and the tail entity would have the lowest learn rate. So at 1.0 or 100%, the head entity will have the highest learn rate. So it will look something like it's so hard. This. Anything like this. Usually it's the current population, for example 1000, divided by 1, 3, 5, 7, etc. So if you but then again, for example, if you divide 1000 by 1, it's 1000. But I would have to ensure that this is also this is 1. So either divide by 1 or 1000. For example, so I forgot how I did it. Where is it? Come on, show me. Show me. Yeah. So, for example, no, I can't see it. So let's just do this again. So if I divide 1000 by 1, I get 1000. But I need to also convert this 1000 into a 1. If I divide 1000 by 3, that's going to be 333.3333. And then next is 1000 divided by 5, which gives us 200. So yeah. So I divide each one of these values by 1000 again. I know mathematically it'll be like 1000 divided by 1 and divided by this. So it's like this. So it'll be 3. It'll be 5. Yeah. So it's 1 over 1, 3 over 1, 5 over 1, all the way to whatever over 1, or 2n plus 1. Is it minus 1? Yeah, it's 2n minus 1. So that's how it is. So this is head favored, tail favored. So again, we have 1 doing it random, 2 ways of doing it proportionate, 2 ways of doing it exponential. There. And again, the last one, normal distribution. So we have the world here again, and we have the head entity, we have the tail entity, but it's kind of important to keep in mind that the head isn't really the head. The head will be one of the newborns, and which is due to the fact that they are added at the front before shuffling. So towards the very front are all the newborns. But anyway, it doesn't really it doesn't mess with the whole evolution, because the newborns are supposed to be slightly better or somewhat better than the pre-existing head or top 10 entities or top entities, whatever, which are from the previous generations. So the fourth one, in this case number 4, would be normal, and that would be ensuring that the median entity would have the highest learn rate, and both ends would have the lowest learn rate. So something close to 0 again. I know I should put that here. 0, and at the highest it's going to be 34% or something like that. Yeah. Now, one thing that is important, again, another thing that is important to mention is that in this case where I'm altering or modifying the learn rates for each individual entity, then this is on the premise that the candidates have been chosen, because as I've said here. So a good way of doing this would be just choosing or choosing the candidates at random, because I would like to see the pure effects of doing this, of doing all of this. So before I assign the learn rates, random learn candidates, the list of random learn candidates has to be made. Or I could just have every candidate learn, which would be included here, because if I were to choose the learn candidates at random, again it would be from 0% of the world entities all the way to, well, to 10%, 20%, all the way to 100%. So I will be able to see the effect of this as well included. And when this is all done, I could probably do all of this again, do the rest. Or I could just, since if you think about it, I need to do this. If I were to do all of this by randomly choosing learn candidates, which is this one right here, then I could naturally move on to this, and this, and then this, and then this, and then this. Yeah. And just compare all the results, which are namely lifespans, compare lifespans, entity distributions, slopes, positive slope ratio, summed utility scores, well, summed utility plots. Is that it? Yeah, that's about it. Oh yeah, the entity counts as well. Entity counts. So yeah, I think that's what I'll do. So, well, that's about it for today, or tonight. The date time was 2025, May 12th, and the time is 04:32, or 32 past 4 a.m. Thanks for listening. Goodbye.